Good morning, good afternoon, good evening, depending on where you're joining us from. Welcome, everyone. For those of you who are new, hi, my name is Maddie Watt, and I'm the Senior Manager of People and Programs at the Hive, and I help lead the Hive think tank. And for those of our returning databees, welcome back. We've got such an amazing event for you today. We are going to be getting down and dirty with data systems and real-time analytics with none other than the co-founder and CTO of Rockset, Dhruba Borthakur. I'm so sorry.
Borthakur.
Thank you, Robbie. Thank you, Dhruba. So guys, let's just get into it real quick. I'm going to go over the ground rules for today's webinar and just tell you about a couple of things we've got coming up for you guys. And then we're going to go jump right into today's event. Real fast, I would love to hear where everyone is joining us from while we get our slides pulled up. I'm personally in the Bay Area. So if you want to go ahead and drop your location, please go ahead and share it in the chat. And without further ado, here's about the Hive Think Tank for those of you who are new. So the Hive Think Tank is an ecosystem of entrepreneurs, corporations, and thought leaders. And we are bringing you events about every other week. And we're also bringing you content pieces on our Medium blog. And we are focused on all things AI and data and all things related to digital transformation and innovation. We are so proud to have hosted over 300 events. We have over 11,000 databees, and we're continuously growing. We have a couple of great events lined up for you guys, but real fast, thanks to our sponsors. Thank you, Robbie. And that includes Avanta Ventures, Gamuda, SAP, and TIBCO. Tomorrow, we are actually proud to present an event with our partner at Hum Capital. They are going to be doing a webinar series on fundraising, and I will drop the link for that in the chat. And then we've got two of our own events coming up for you guys. Very exciting. We are going to be talking about sustainability and leading brands. And this is going to be a very special panel with some of the boldest brands in the space. This is going to feature the CEO of Nespresso and the global head of and general manager of HP Supplies from HP Inc., along with a senior partner of Kearney. And we are going to be deep diving into brand identity, implementing innovation in terms of sustainability, and revamping yourself for this new normal and this new world that we live in. So please sign up for this. I will be posting that in the chat, and this is going to be on Thursday, December 9th. We are so excited to be teaming up with these members. And also we have another event for you guys on the 14th. If you are on the other side of the world over in the Asia part, but if you are in the North American part of the world, you will be having this event on Monday, the 13th. This is going to be with our partner Gamuda, and we are going to be focusing on the future of cities and tunneling and underground and what urban planning looks like in the future. So this is going to be a very special event with some of the leaders in this space, people that have been doing these things for the top level people, such as Robbie, I believe the company is the Boring Company, correct? For tunneling?
Yeah, so no, so this is an exciting event, you know, as urbanization continues to grow. We are running out of space above ground, and so there's a lot of people, smart people, imagining living spaces, parking spaces, workspaces, transportation underground, and Gamuda has been an innovator in autonomous tunneling, and this is especially, I would say, challenging because in areas of Southeast Asia, the ground is unstable, and doing this safely is difficult. So this is going to be a very exciting event. So I hope you can all join.
Exactly. So, and thank you, Robbie, for building off that. So I will post the links for that in the chat. Without further ado, here's Tim Robbie, the managing director of the Hive. And just remember, guys, we do love questions. So please use the Q&A button to ask your questions. If I see you asking them in the chat, I will have to chase you down and make you use the Q&A button. Thanks so much.
Great. Thank you, Matty. And so very briefly, the Hive is a venture capital entity. And in particular, it's a subclass of venture capital that's called a venture studio. We are very active at the seed stage, fund either existing kind of companies along with a seed syndicate, or we collaborate with founders to help them start companies. And so you can see some of our thematic areas, some of the industry segments that we are focused on. And so common to all of this are the underlying technology. So as Matty had mentioned, our main focus is around leveraging data and data-related techniques to create new opportunities and drive disruption. So if you're an entrepreneur with a company or an entrepreneur who wants to start a company, please do reach out to us and we'd love to engage with you. Since sort of the early days of the Hive, we have created, we are on our 4th fund right now in the US, but we have created separate entities in India, Brazil, and more recently in Southeast Asia, based in Kuala Lumpur. And we are exploring the Hive in Europe for some time mid next year. With that, I'm very pleased to have today Dhruba Borthakur, the co-founder and CTO of Rockset. We've known Dhruba for a long time. He has participated and moderated a number of events. Remember the kind of heyday of Hadoop, where I remember one event called Riding the Elephant, where more or less people came to blows with each other. Those were exciting times. Unfortunately, Hadoop didn't quite make it the way many other data management, data quality, database, warehousing companies have made it in the last few years. This has been somewhat surprising, but extraordinary sort of time for data-related companies. Dhruba has a long history in the data and data management space. Did a lot of work at around Andrew file system at Transarc, which I guess later became IBM Transarc, and subsequently at Veritas. I may be missing some of the things in your career. Was at Yahoo during the heydays of the development of Hadoop. And then subsequently at Facebook and now founder of Rockset. So please ask your questions using the Q&A button, and with that I'll hand it over to Dhruba.
Hey, thanks, Ravi. Really appreciate it. Thanks for the introduction. It's great to be here. I have been associated with the Hive for a long time, and I probably know some people in the audience, but not everybody. So thanks for coming. I hope we can have a good, engaging discussion today. And please submit your questions or ask me questions, interrupt me, so that I can make this presentation more useful to you rather than going through all my slides. I'll share my screen. Give me a second. Okay. Great. Hey, welcome. Welcome to this talk. Today, we are going to talk about how data systems have been evolving over the last 10 or 15 years, and how it is coming to today's time and frame where things are becoming more real-time, and there is a renewed focus on using data for some real-time analytics. So that's the topic of my presentation today. Again, I would rather make this a discussion rather than a presentation. So please interrupt me and ask me questions when you have something in your mind. A short introduction about myself. Again, right now I am a co-founder and CTO at Rockset. Rockset is a cloud data service for doing real-time analytics. And prior to that, I had worked on these software systems that are listed here, essentially RocksDB. That's a database I built when I was at Facebook, and then I played a very early role in the Hadoop file system, HBase, and these kind of systems. These are all data systems that I have been building for the last 15, 20 years. So today's talk, again, I'm going to give you a little bit background about my perspective. So this talk is kind of opinionated in the sense that it presents scheme of things on how I have experienced it from very close by. And I try to tell you some of the evolution that has happened. I'll also focus on more of the real-time nature of data that has come into being in the last maybe 2 years or so. And then I'm going to deep dive a little bit on some of the technical aspects of how you can build a real-time data system yourself with your data, with your use case. And then I will have a Q&A, but again, ask me questions in the middle of the talk if you'd like to. So I have been associated with Hadoop for a long time, like Ravi said. Hadoop started back in like 2006. I was part of the Yahoo team at Yahoo, the engineering team. I think I was the third person in the team. I was building Hadoop file system, and that system was very much a big data system, or kind of the granddaddy of all big data systems. It was focused on mining a lot of data and doing analysis, and all these analyses were batchy in nature. You could run a query for many hours, and it's okay if the queries are slow as long as you can get information or get value out of your queries. Over time, then people have migrated to more streaming systems. Streaming systems are things like, say, Kafka, where you can kind of write data on one side and stream data from the other side of the pipe, or Spark, where you can do kind of ETL processing. When data comes in, you can process data and make intelligence or make sense out of it. Latencies obviously got reduced from what Hadoop used to. Hadoop used to be very batchy. Spark, Kafka, there you probably get insights into your data of latency of, say, minutes to hours. And then over the last 2 or 3 years, there's a good focus on being actually real time. Real time here means about, if I have a data that I just captured, how can I act on that data within a few seconds, or maybe 10 seconds of it being generated? How can I make decision processes so that I can make my data systems very reactive in nature? So that's kind of the overview of the evolution of how the data systems have evolved. Now, if I go back to my Hadoop days, I will give you a great example of how powerful the Hadoop system was back in the day in 2005 or 2006, or maybe somewhere around there. So I was closely associated with this application called Pymk. It's People You May Know. It was an application that Facebook was developing at the time. You might hear a lot of controversies about this application today, but back in 2007 and 8, this was one of the most fun projects I ever worked with, right? So Facebook was a social media app, and it was just starting, or it was very early days, and there was a lot of competition from other competitors. And this is one project that really made Facebook be very viral. So what is Pymk? Pymk is People You May Know, which basically means that when you join Facebook the first time, the goal of the software is to suggest you friends, people who have the same tastes, people who live in the same area, people who went to the same universities. So there's a complex logic of figuring out who could be your possible friends. And when a person logs into Facebook for the first time, the system suggests him people that he can be friends with. This is the key to going viral. And this is one of the basic building blocks that Facebook designed very early on. This was a very data-centric system. It had to process a lot of data. These processes were very much complex in nature, but they're also very batchy in the sense that you could do a lot of analysis yesterday and then use the results today to suggest friends to your app or to people who are joining the app. This was way back in 2007, I think, where Facebook had maybe 5, 10, 15 million users. Over time, these batch systems, although they were very good and impactful, people started to migrate to more streaming solutions or being more real time. Take, for example, another use case at Yahoo, ad optimization, right? So Yahoo is an advertising company, and the goal for the company is that how can you show relevant ads to people on online ads and get value for their customers. So what happens was that in the beginning, this was, again, I'm talking about age of 2006 or 2007, 2008, during that time frame. Yahoo used to have 26 properties. So Yahoo Finance is one property, Yahoo Email, Yahoo search is another property. So all these properties, people run campaigns to show ads. And then when you submit a campaign, you tell the system saying that, hey, I want to show 100 ads today. And then when Yahoo shows ads, they need to count how many they have shown. And when 100 is reached, they want to cap the daily limit of that ad, right? This is standard ad placement, but I'm talking about this way back in 2006 or 7 when things were very elementary in nature. And then Yahoo used to have this delay of like 1 day before the counters get aggregated. And so there's a lot of overspend in the system already shown too many ads compared to what the user has paid for. And then when Yahoo reduced these by using more streaming systems, where the data lag became around an hour, the 200% of overspend was reduced to 20% of overspend. I remember this because it was a big deal at the time, saying that, oh, this is a great way to reduce overspend. So these were 2 historical examples I gave. But now I can talk about more real time and how things are evolving over the last 5 or 15 years, 10 years now. So here's a use case where you have a real-time fleet management system. You have 7,000 trucks delivering goods from one place to another. They could be food items, they could be industrial construction items, there could be cement from one place to another. And then there is sensors in the truck, which talks about the temperature of the truck, the temperature of the engine, other characteristics of the items being carried in the truck. And these sensors upload data to the cloud, and there is a data system which is processing these sensors and figuring out what is the best way to route these trucks. And the moment there is a coolant problem, you know that the goods will time out after or perish after 1 hour. So you need to redirect the truck to the right place, make sure it can go to the repair station. And here the focus is when an event is created, how can I quickly act on this event? I can't wait for an hour for me to make a reaction for that event. I need to do it within a few milliseconds or within a few seconds. So it has become much more real time. This is a use case that I see very close by, which is why I took this as an example. Here, the data latency and the reactiveness is a few seconds from when the event is produced. Similarly, another great example are a bunch of real-time analytics in gaming. So when you're playing a game, an online game, there is a lot of matchmaking. There's a lot of relevance or matching users to which games they should play. And again, you need to find similar games with similar tastes and being played by a similar level or competence of players at a time. Because if you recommend that game to this person, then this person will enjoy the game the most. He doesn't want to play a game with super high competitors or somebody who is much more novice in the game, right? So there's a complex matching algorithm, and this matching has to happen as soon as the user logs into the system. This is an analytical system, and the analytics have to happen within, say, 5 seconds of the user joining the system. Similarly, leaderboards. You want to create a leaderboard on a game on 500 different characteristics. And then the leaderboards can be 10 minutes lagging. It depends. The moves that you make now in the game needs to be reflected in the leaderboard almost immediately within a few seconds. This is again another example of real-time analytics in gaming. Yet another example that we see are things like real-time analytics in computer vision. So I'm going to play this video. I might not play it for the whole time, but I will leave it on for so that you can keep seeing when I talk about it. This is checkout system, automatic checkout. And there's a video camera that is taking pictures of people picking out things from a retail shelf. And it's figuring out so that there's analytics that runs on the video stream to figure out what is the person that's picking from the shelf. And then the person puts that in the cart. And when the person goes to the checkout center, he's automatically presented a bill and he doesn't have to scan every item to check it out. This is automatic checking. Again, here the complexity is very high because there's a lot of computer vision related things, but there's also complexity in the thing that once you convert a video stream into a set of tags, how can you match them quickly? Again, real-time analytics where you're talking about maybe a few milliseconds of latency. before you can decide what is the item that the person has picked. And this is a very complex algorithm that is, or model that's being run in the background. So I'm going to pause that because I just wanted to show you a little bit idea about how real-time analytics are also being used in vision or computer vision related things. The interesting thing in my mind, or the common theme among all these, is that building these real-time analytic systems are hard. They're not easy. They sometimes need a lot of compute. Sometimes they need a lot of data. Sometimes they need to have great models to be able to do them within very short periods of time. But the rest of my talk today is focusing on, if you have these kind of analytical systems or real time, and you want to make them real time, can I help you in understanding them better so that it becomes slightly easier for you to manage these systems? Again, because not much has been written about real-time systems in the prior years. It's a very emerging field. And so my goal here is to kind of declutter some of the data systems that are out there and help you guide or help you figure out how you can make your own decisions on how to build a real-time system for yourself. Again, if you have questions, please ask in the Q&A. I'll take one question here from Jim. He says that for real-time analytics, do you prefer streaming only solution or combination of streaming and batch? Great question. It depends on the use case. I think there are certain things that are possibly going to remain as batch systems, but then a majority of new things that you can do streaming only solution is great if you can balance the price performance of your solution. So everybody likes streaming, right? If possible. It depends on the price performance. So I will touch upon this answer in more detail as part of my slide. Great. So there are many data systems out there that claim, all of them claim real-time analytics. So now the question is that which one is good, which one is good for your use case is what I'm going to talk about today. I'm going to analyze some of these systems based on their usefulness for being a real-time system. Again, please don't get me wrong. Each of them are great data systems here, but how good are they for real-time analytics is the question that I'm going to try to answer today. I'm going to analyze them from a set of 8 perspectives or 8 items in my checklist. And I'm going to explain why each of these items are useful for real-time analytics. And then I'm also going to give you an idea about how those data systems that I mentioned perform in this checklist of each of these items. What is kind of their grade? How do they actually perform in each of these items? Make sense? Again, please ask me questions. Keep the Q&A questions coming so that I can answer them as and when I'm giving the talk. So the first thing that comes for a that needs to be thought about when you are building a real-time analytics system is bursty traffic, which basically means that things could be slightly unpredictable, or you cannot really predict what is happening in the future. Take, for example, the great example here is the Amazon Prime Day 2015. This was the first year that Amazon had this Prime Day. They usually have, like, let's say 40,000-50,000 visitors per day. And on that day, they had double the amount of visitors. This was by design. This was not like a fluke, but they did not, I don't think, at least their blogs seem to say that it wasn't that they predicted exactly how many users will be there. They know it will be more than their standard, but this is what I mean by bursty traffic. Now you have a backend system that works every day in and out, but then suddenly twice the amount of load comes into the system. What do you do? How do you design it so that it doesn't fail? So one thing that this use case did right for Amazon is obviously they're designed for the cloud. They use a lot of AWS services themselves. And there was no need for them to kind of over provision a lot of compute or storage or hardware or machines up front and trying to predict how much they actually need on that certain day. They also needed a disaggregated architecture, which basically means that you can kind of decouple the storage and compute of your data systems, so that depending on the bottleneck, you can scale that angle up as and when needed and scale it down also when it's not needed. So cloud native disaggregated architecture were key to ensuring real-time systems are affordable and they can scale up and down when needed. Disaggregated architecture is sometimes difficult to kind of wrap your brain around, like what is really a disaggregated architecture? So I thought I will kind of relate it myself to how like the human body works, right? So let's say you have a backend data system that has some compute like CPUs for processing, and then there's data to be stored. Now, that compute that I'm talking about is very much like the human brain, right? Human brain is the intelligence of the body. It's kind of processing a lot of data and then making decisions based on that data. And to make the brain work well and to make it perform better, you need to do a certain set of exercises. There's a brain puzzle, Sudoku, whatever else you might do, but they're very different from the things that you would do, let's say, to kind of make sure that your storage is performing well, or you can add more storage to the system when you need it, because the storage is very much like the human body. To make the human body powerful, you might need to do a different set of exercises. You have to do physical exercises, and both the mind and the body has to work together to perform well when there is adversary coming your way. So this is the same thing with a disaggregated architecture. Here, compute and storage have to work together, but they're two separate things. So we need to think about those two things separately and see how can we exercise each part of it separately so that they can grow and shrink as needed based on the workload that you have. So one of the standard ways for real-time systems to use a disaggregated architecture is something called the aggregator leaf tailor architecture. So again, this is a standard architecture that is starting to become popular in the last 3 or 4 years, or maybe 5 years. I will tell you a little bit about the architecture of this, or the technical dimensions of this architecture, but then I'll also tell you the history of this architecture. So this architecture, the technical distinction or the uniqueness of this architecture is that it disaggregates 3 things. It disaggregates the storage from the compute that is needed to make queries. And it also disaggregates the storage from the compute it's needed to write data to the system. So unlike traditional or cloud warehouses, where the disaggregation is mostly between compute and storage, here the disaggregation is compute needed for queries is disaggregated from compute needed from indexing or writing, and it's disaggregated from the storage. So it's a 3-way disaggregated architecture. And this is the reason why it's useful for real time, because real time you have writes as well as reads. Whereas in a warehouse, which is disaggregated 2 ways, there's mostly read-only data, so there are no new writes for the system. So this is why the ALT architecture is super important. So you'll see the tailors which are needed to write data to the system. Then there are the leaf nodes that store the data in the system. They're separate from the tailors. And then the blue boxes that you see are the aggregators that are needed to query the system. So if the volume of queries increase, you just scale up more and more aggregators. If your amount of data increases, you scale up the number of leaves. And if your write rate increases, if you're writing more data to the system, then you increase the number of tailors. So this is the 3-way disaggregated architecture. And write compute is separate from read compute, which is another critical dimension of how this architecture is different from previous architectures you might be familiar with. Now, we didn't invent this architecture. This architecture we kind of started to use at Facebook. So this is I'll give you 2 examples of how the ALT architecture evolved over time. So Facebook used the Facebook feed, the news feed, right? When you log into the Facebook app, you see the posts, comments, likes of your friends. So that is actually a real-time analytics system, right? It's not a transactional system. It's not like credit card subtracting money from one account and adding money to the other account, right? It's a very much an analytics system, which is doing relevance matching, sorting, aggregation, and then showing you the top 10 items that the system thinks you'd be interested in based on all the posts from your friends, right? So this feed, this is called a Facebook feed. So this feed used to be generated in a different way earlier, where the feed will be generated, and then when you log in, you see whatever feed was pre-created for you. But then over time, Facebook moved to this architecture called the ALT architecture, where the feed is generated on demand, and it uses the ALT architecture on the back end. And when you log in, the feed is not pre-created. The query is made right then and there. It goes through your entire inverted index, or the index that you have built on your data. It makes a low latency query on this large data set and gives you the feed within a few milliseconds. So the advantage of this, the ALT architecture for Facebook was that engagement just shot through the roof, because if you see your friend's comments, the moment it's posted, it gives you more engagement in the application compared to if your friend posts something and you see it after 10 minutes, then the engagement goes down. So being real time was super important for this use case, and Facebook used the ALT architecture to power this on large data sets. Similarly, I was working with some engineers in LinkedIn at this time. I think this is around 2011 or 12. Where they kind of used the same ALT architecture for the LinkedIn follow feed. And that follow feed, I think they used a system like Sensei, or they have written a blog on this, so you can read this as well. It will be in my slides, the link to the blog. But they also explain why the ALT architecture helped them make the LinkedIn feed more real time. So again, the thing that I kind of summarized in this first checkpoint or bullet list is that if you're building a real-time system, then making sure that the data system that you're working, does it follow the ALT architecture? That'll be a great way for you to analyze the data system that you're building and see if it is useful, if it is purposeful for real-timeliness of your data. So that's the first item in my checklist. The second one is complex queries. So what is a complex query? And what does it actually mean, complex queries? So I'll give you an example. I'm talking about an example that came to my mind when I was working with Hadoop at Facebook, probably around 2009 or 2010. There was one of the first financial companies that started to use Hadoop was Morgan Stanley. And I remember talking to a few great engineers in the Morgan Stanley team, and they were trying to get a lot of mortgage instruments into Hadoop and trying to build a model so that they can customize or personalize the loan rates that a corporate customer is trying to take a loan from them. What is the exact loan rate that they can provide to that customer based on the risk factors, based on historical analysis, based on publicly available data. So here, the queries that they actually made were on Hive, on data stored in Hadoop. And the queries are very complex in nature. There's a whole pipeline of queries that need to run before the results come out. But when I talk about complex queries, the complexity of this algorithm just blew my mind at that time. This was, again, things have become much more complex now, but I'm talking about a use case that I was very familiar with. These complex queries mostly dealing with aggregations, which are like summing, averaging, sorting, finding standard deviation, and then also joining. So joining data between two different data sets. So joining, these two are super important for your systems being real-time in nature. If you don't have joins, then you have to have a lot of code in your application to do an equivalent one when you need it. So implementing joins in some data systems is hard, because take, for example, you have two different tables and you want to join them because you want to find the intersection of these or the intersection or the union of these two tables. The intermediate data set could be very big. For example, here, I think there are like 50 and 150K records. So if there are NNM records, the intermediate data size is super big. And then just imagine if there are 10 tables that you would need to join, then there's data explosion. That's why a lot of data systems don't support joins right now. So this is another good thing for you to investigate, is that the data system that you're using, does it support joins? And that's the answer to that might influence you to pick the data system for your real-time analytics or not. Take, for example, in this case, is the data system, let's say you're making a query and finding recommendations about movie recommendations. the data system has to push down the predicates to the deep inner level of the query, should be intelligent enough to push it down so that the joins come back, answers come back quickly and in real time. So this is a great way for you to compare and contrast to different data systems and find out, do they implement joins? And if they do, how fast are the joins? Because this is super useful for building real-time applications. Sometimes it's difficult to do this when you look at two different data systems. Take, for example, these two birds that, so I live in a very wooded area and I take these walks in the park. And sometimes there's one time when I saw two different birds, well, actually two birds on two different trees. They look exactly the same from far away, but they were not actually same. They looked the same to me. It's just like two data systems sometimes look exactly the same when you look at it from far. But then when I went closer and closer, I saw that one was actually a crow because he started to speak and then fly away. But the other was a cuckoo. And then the song that you hear from the cuckoo is like really beautiful. So this is what I mean by a system which is a data system which supports joins and a data system which doesn't support joins. If you pick a data system which joins, your analytical needs, especially for real time, becomes really sweet and useful. And you'd find it going forward when you go deep dive into your use case. This has also been validated by many data systems that are out there because SQL and joins have become more and more important. Kafka has now KSQL, MongoDB is trying to implement a SQL API. So this is kind of validated by just market commercial systems as well. Also, if you look at Stack Overflow, people prefer MySQL Postgres just because it's easy to use, because it's SQL, and it's very expressive. It's a very powerful language, and it has joins, which basically means that you can combine two different data sets and make sense out of them immediately. So again, this is the second item in my checklist, is that if you're picking a real-time analytics system, deep dive into each one of them from close and see, does it support joins? How complex, how quickly are the join algorithms that they have implemented? Because the key to making your real-time application be real-time is that joins need to be supported, and low latency joins are a sweet deal. So that's the second one. The third one I talk about in my checklist is flexible schemas. What is a flexible schema? So again, going back to an example that I had that I worked with in very early days, it was called Project Nectar at Facebook. It was a project that was created to have logging of every Facebook user's interaction with the Facebook app in a standard set of attributes. As soon as you ship this logging system and we're collecting a bunch of logs, the first question that one of the application developers asked us is that, can you change the type of the column? We were maintaining a column called time spent in seconds, and he asked, saying that, hey, can we change it from seconds to milliseconds? So now the type of this column changed. So this is what I mean by flexible schema. How quickly can you iterate on things where column schemas change very quickly? So what is a flexible schema? Flexible schema sometimes look messy, like the picture on the left, but it gives you a lot of agility, and you can really move fast if you can handle flexible schema data. This is basically a no-brainer nowadays, but again, not everybody has jumped onto the flexible schema bandwagon. Again, the reason being is that for flexible schema, sometimes there are complexities of querying this, because if you don't know the schema, how do you actually build a query to get data or intelligence out of this system? Again, a small digression here. So Rockset has built something called smart schemas, which basically means that you get the best of both NoSQL worlds and SQL worlds. You put data in a NoSQL format into the data structure, into the database, and then you can quickly make SQL queries out of it without creating a schema, because the system makes the schema for you. I don't want to deep dive on the Rockset part, but please feel free to look at rockset.com, and there's good write-ups on what to do it. What do other data systems do for providing flexibility? So one data system, Postgres, very widely used. It doesn't really have schema flexibility. If you need to add a column, you have to do alter table. And there are some things you might have to take offline to be able to do alter table. Cockroach DB, again, great data system, mostly optimized for transaction processing. And you can do few schema changes without bringing down the system. But there are, again, certain limitations. And Hive, obviously, the most flexible of all, where you can have free format schema, but then the queries might be slow because you might have to use this Hive SERDI and or deserialize the data as part of every query. So again, different trade-offs, but this is a great point for you to think about. How can you have flexible schemas when you're building a real-time data application? Does your data system, the one that you pick, does it support flexible schema so that you can get your work done quickly and never lag behind and lose your real-timeliness of your application? Again, if you have questions, please do post in the Q&A. Otherwise, I'm going to chug along and go on to the other items in my checklist that I have. Okay, so let's talk about the third or the fourth. Maybe the fourth item in my checklist. So what is the fourth item in my checklist? It's about low latency queries. So being a real-time system, you need low latency queries, right? But then the challenge as a data practitioner is that almost every data system will say, oh, I support low latency queries. So how do you separate the wheat from the chaff and figure out, is this really a system that can provide me low latency for my real-time applications? So I will give an example. So I picked this book, Harry Potter, because it's lying on my shelf these days. My daughter, when she was in middle school, she used to read this entire book multiple times, or this book series multiple times. It was her favorite, so I picked this one. And there is this phrase here, you know who, that reappears in many pages of this book. It's a phrase that's a pseudonym or whatever you call it, for instead of referring to Voldemort, it talks about you know who. So now let's say you have this book and you're, and as an as your application, application programmer, developer, you need to find out all the pages that this phrase appears. So the left side of your screen, you see one way to do this. You scan every page, finding this phrase and then record them. The other option to find the same thing is to go use the index at the end of the book. So every book has an index that are the last few pages of the book. So you go to the index is organized in sorted order. So go find this phrase, you know who, and then we'll have a list of all the pages where this phrase appears. So now think about this query, right? Finding the pages where this phrase appears. If you use the scan method, you would have to spend a lot of brain power and time searching through them. Whereas if you use the index, it is probably instantaneous. So this is the key to making databases fast. Databases use indexes to make queries fast. This is kind of one very well-known standard for databases, is that how can you make indexes or build indexes so that queries become faster compared to full scan. So obviously you can build many types of indexes. You can build a columnar index where all the data in a column are put together. This is what a traditional warehouses do. You can also build a search index, just like Elastic or some other search databases where there's an inverted index and you can really do high selective queries very quickly. So building indexes, again, is something that you should ask your data system. Does my data system build an index to make queries low latency? Just if the data system says, I make queries low latency, it's not that useful unless they also tell you what is the technology that they use to make these queries low latency. One great example that I worked with in early days was the Facebook Dragon project. So Dragon was a Facebook inverted index that they built on the entire social graph. The entire graph was first keyed by the person who made the post and set of like the posts that a person has done. But now if there's a query saying that, find which of my friends from London posted something about Harry Potter. Now you don't want to scan the post of every of your friends. You want to have an index based on the location and the content. So if you have an index, you can quickly find this out. So this is another big indexing project that I have worked closely on a large data set, and that really reduces, and I could see how it reduces the query latency of a lot of Facebook queries at that time. So indexing everything is the key to making kind of almost every query fast. And this is very useful for real-time analytical applications. I'm going to skip the slide. Again, so just to summarize, to kind of capture the point that I was trying to make for this bullet point is that traditional systems mostly do like a parallelize and scan approach, very much like for a historical artifact like MapReduce, where you can scan a lot of data and quickly get results. But if you have converged indexing, where you basically build a search index and columnar index together, that is what you would need for serving real-time analytical applications, because it's not parallelize and scan anymore. The new way of getting real-time applications, powering real-time applications in parallelize and index. So this is another question you can ask to the data system that you are using. Do you folks do, does this data system do parallelizing and scan to give me results on large data sets, or does it actually build an index so that my queries are faster? The fifth point that I usually use to decide what system to use for powering my real-time apps is it a mutable data system? So what is a mutable data system? Again, I'll take an example from prior history that I have worked with. It's like, let's say, the Facebook event record. Now, this is an event that I picked. It's a whale watching trip, right? And it says that it's on December 31st or December 30th of this year. I was thinking of going whale watching, but then how do I know that this is actually a valid event? Usually whale watching is like November to March, or kind of March to November, and there's usually nothing in December, but this event popped up on my feed. And so now this could be a fraud event, because sometimes bad people are trying to get data out of the system. So Facebook has a lot of machine learning algorithms to be able to figure out, is it a fraud or not? And then once they find out that's a fraud, they need to be able to mark that event saying that it's fraud. So you need these events to be mutable. If it is not mutable, then how would you do that? You have to record it in a different place. For example, let's say all the events are in this data, and then your machine learning model finds out that one event is bad, then it has to go write it in some other place saying that these events are bad. And so now when you're making a query to render your feed, you have to look at these two places. Your application has to look at these two places to find out, is this a real event that is valid and not a fraud event? So this is the challenge when you're using an immutable system for doing real-time analytics. You need a system that can actually be mutable and has the ability to update every field if needed on your event, so that you can mark it as spam or annotate it or do data enrichment in place instead of doing on the site. So again, here the example is like, let's say there are 3 events and all of them are marked as spam 0. They're not spam, but then once you mark it, you can edit one of them and say, hey, this is a spam event, the last one. So there's no look-aside buffer. There's no other data referential integrity problems that arise. I'll skip this slide for now. The last one, or somewhere close to the last one, is this checklist item that I have, where does your data system support out of order events? So what is an out of order event? Out of order events are usually like a lot of real-time data analytics looks at event data, right? Events have a timestamp, they're coming in. Usually the data system partitions your events into different areas. Let's say here it's bucketed from 9 to 12 a.m. and then 12 to 3 p.m. is another bucket, and they put all the events together. But now, what do you do? Now these are packed together and queries run on these partitions. But then what do you do if an event arrives out of order? And this is a real life problem, right? This happens all the time. Let's say, again, going back to our fleet management truck example, if a truck's sensors are gathering data but not able to upload it to the cloud. So you might not be able to upload it to the cloud for a while. And then when it does, now it needs to insert this event right in the middle of a partition that was already kind of closed and sealed by the data system. So now your data system has to somehow handle this so that if a new event comes backdated, it can fill it up and put it in the right place so queries work well. And some data systems don't do this very well. So you'd have to, they will put all the updated events in a separate place, or out of order events in a separate place, and you have to query these two places. So your application has to look at two places to figure out all the data. So which is why if you have a mutable system that can handle out of order applications, that is what will make your life of your application developers easy. The last one that I'm going to talk about today are rollups and summaries. So what is a rollup? So streaming data, we're talking about building real-time analytics on streaming data. So streaming data, usually there's data coming in a small stream or some well-expected velocity of data, but then suddenly sometimes data comes in a storm. And then is your system built so that you can handle the large volumes of data as well. One way to handle this large volume of data is to do rollups when data comes in. So when data is coming into your system, is there a way for you to summarize and reduce the amount of data instead of writing everything out so that you can keep on the relevant portions of the data that you think are interesting to you? I was trying to think, one of the first time I actually heard about rollups. And what happened was that I joined Facebook back in 2007 or 8. And this person, Jeff, he was my boss at Facebook. He was the creator of the data system at Facebook. And my goal, the first 6 months or whatever, was to figure out how to expand the Hadoop system so we can store more data. And then one day he comes and says that, hey, Dhruba, why do you store more data? Is there a way for us to kind of summarize all the data when they're coming in and store only the things that are real value? So that's the first time I actually heard about rollups. He didn't use the word rollups, but he was actually talking about rollups. And so rollups were needed. I'll give a simple example of why rollups are needed. Now, take, for example, Facebook. Their one goal is to figure out how many active users are in the system. There are daily active users, monthly active users, all these kinds of matrices, right? So daily active users, the interesting thing about daily active users is that there was a counter that we needed to generate, which wanted to count the number of daily active users per country and per state. Now, at today's day, I think there are 2 billion Facebook users. And if everybody logs in 5 times a day, that's like 10 billion events. Do we need to store all these 10 billion events? Probably not, right? And because the queries we are making is that how many, we need this value per country and per state. So does anybody know how many countries are in the world? I think there probably are like 195 or 200 countries in the world. And then every country has a few states or maybe a maximum of 100 states. So if you have these counters, you need only 1,900, 5,000 or whatever, 19,500 counters. So when the data comes in, you find out the relevant counter, you update it, and then maintain only these counters. So instead of storing 10 million records, now you just need to maintain 19,000 counters. So this is the power of rollups. And your real-time system needs to support rollups so that you don't store data that you really don't need to, right? Because the data volumes are high. And again, going back to the aggregator leaf Taylor architecture, here what happens is that rollups are supported by the tailors because they're separated from the storage and the query engine. So what happens is that when data comes in from all these sources, Kafka, whatever else, other data sources you have, the tailors actually call into the aggregators, summarize the result, update the counters, and then update these counters in the storage system. So this is how rollups are implemented. One way for you to figure out whether your data system supports rollups is obviously to find if this feature exists in the data system that you're using. You can also think about how easy is it to use. So rollups typically are specified as SQL queries by some systems. So this is the query that I have in the middle. All the records coming in from the back left side, it uses the rollup query and summarizes it into 2 records that need to be stored instead of 3. So this is a great example for you to kind of evaluate your data system and see, does it support rollups? Does it allow me to express my rollup queries using SQL language? These are the questions for you to ask when you're picking a data system for your real-time analytical needs. Exactly one semantics. This is the last item on my checklist. Essentially, you need all your data to be sent only once and counted. Otherwise, you'll double count some of these data in your roll-up processing, which is why exactly once is another thing that you need to be cognizant about when you are using your data system. So that's kind of the checklist that I have today. The checklist, what I tried to do was to kind of explain how things move from batch to real time. And then I kind of went through, we explained some of the use cases that is very appealing for somebody to understand why real time is useful. And then we also went through a stack of or a checklist that you can use to figure out how to build your own modern real-time data stack to solve the real-time analytical needs of your application. Rockset does this, obviously, which is why that's the business we are in, where we support a lot of these features or the checklist items that I have. Please feel free to go to rockset.com and try it out or see it. I think there are one or two questions. Let me take one question. What are some other growing trends in analytical needs? Great question. So trends in analytical needs. So there's a lot of things about machine learning analytical needs where you have to make sure that the models that you're running for serving production data are explainable and can reason about. So there's big amount of work going on in that area as well. Hey, Ravi, do you have any questions that you'd like to ask?
No, I think there are a couple of other audience questions. Maybe you could catch some of this.
Sure. Yeah. I can take another one. Let me check.
Yeah.
Yes. Do you have an opinion on graph databases for real-time applications? Yes. Graph databases are super useful. I just want, when you're talking about graph databases, I think it's great to know whether you are using graph serving or graph computation. So graph serving is different from graph computation and figuring out clusters in your data. So one is very much a batchy system, whereas when you're talking about graph serving, that is definitely something that is useful for real-time analytical needs. So graph databases are super good. Most of the graph databases I've seen are useful mostly for the backend clustering algorithms rather than graph serving. So you'd have to figure out, when you're talking about a graph database, what is your use case? Is it graph serving or is it graph computations and graph clustering algorithms? How do you handle data consistency between upstream data sources and real-time data sources and real-time analytics? Great question. I think this is something that you'd have to define yourself. Let's say your kind of, it's a nebulous area, so it's not very well defined. If you have any opinions, please let me know as well. I would like to know. Right now, most of the data systems are kind of eventually consistent, but you can implement some of the consistencies by using commit markers and sequence numbers that a lot of these streaming systems do, but you'd have to build it yourself, which is one challenge, again, in building an CRUD type of consistency in some of these streaming data that's coming in. How many of these concepts and trends being taught in universities now? Great question. So a lot of the courses that I see are very data focused, and real-time data is just becoming a thing now. So I don't see a lot of these things that I talked about today in university courses. University courses are still in the Hadoop world, where they're talking about big data systems, crunching a lot of data, and the real-time part is yet to come in a lot of the courses. I'd love to collaborate with people in universities to see if we can make some of these things be part of courses and stuff like that.
Maybe Dhruba, one final question. Mm-hmm. You gave a lot of examples and use cases of real-time analytics when it comes to sort of social media, and I guess because you used a lot of Facebook type examples. And
mm-hmm. Yes.
When it comes to other industry segments, sort of is near real time good enough?
Great question.
It's a question that often comes up. And so can you maybe highlight kind of use cases in financial services and industrial areas, other areas where real time is critical?
Yes. So industrial, I can definitely give you an example. I have seen one use case now where there are probably around 10,000 trucks on the road, which are all having a lot of sensors. And then the challenge though is that here they're talking about analytical delays of maybe 5-second delay before they can figure out how to reroute this truck. Currently their work, or prior to being real time, they were having some kind of goods lost or inefficiency in the system. And now when you can actually make it 5-second data latency before you can react, the advantage to that business is tremendous. It's difficult to explain because some of it is based on intuition. It feels like, oh, it doesn't really make a difference if I change the latency from 1 hour to 5 seconds. But this is happening. And then the other one that I see a lot are financial hedge funds. So they're looking at a lot of trends, right? What are people searching, what are people talking about, and they want to make decisions immediately rather than waiting for even like 5 minutes. So again, talking about finance. And then video analytics, again, a great example where real-time analytics is super useful, but these are on the cutting edge. Even further down the road is video analytics is what I think it is now. Does it answer your question, Robbie?
Yes, it does. Dhruba, it's been a great pleasure to have you once again at the Hive think tank, and I speak for Matty also in thanking you for joining us today and speaking, and look forward to also doing more things together with you. Maddie?
Thank you so much, Dhruba and the Rockset team, and thank you, Database, for joining in today. I went ahead and dropped some more links in the chat. We hope that you join us on December 9th and December 13th, and have a great rest of your day. Thanks for joining us today. Take care.
And if we don't speak to you, have a happy Thanksgiving. Thank you.
Yes.
Thank you, guys.
Take care.
Bye. Bye.